for this example we're going to do something similar again that we did with Thomson, balancing some forces, but in this case we're balancing two different type forces. And this is exactly how Millikan ended up doing his experiment, and I'll show you all the various formulas that we ended up using. Let's keep straight off to the side with what we're being given, because this has got quite a bit of work involved with it. We have the density, so we use the Greek symbol for density, which looks like a P, 1.35 kilogram per meter cubed. We have the diameter. Well, the formula is going to end up using radius anyway, so I'm going to actually just convert this to a radius as is. It's 1/2 times 6.05 times 10 to the negative 6 meters. The plates are 30 centimeters apart, so the distance between the plates 0.300 meters. Converted it to meters already. The voltage between the plates 240 volts. We want to know what is the charge, and we also want to figure out the number of charges. Those are directly related to each other. So this is going to involve quite a few formulas. I'm going to set it all up on this slide, and then we'll do our calculation on the next. Since we're balancing electric and gravitational force, that's where we start. Electric force equals force due to gravity. Millikan is always a balance, and here it was being suspended somewhere in here. Oh yeah, there it is. So what we want to make sure is that there's no net force. These are equal and opposite. Well, the formula for electric force between parallel plates is QE. Force due to gravity is mg. So we'd like to find Q, but we don't know E and we don't know M. So we'll start with a formula to find E. We know between parallel plates that is in a uniform electric field, and it relates to V over D. So we'll start with substituting equation 2 into 1. And what you'll end up with is equation 1 will now look like Q, but instead of E, I'm going to write V over D. So it'll be QV over D equal to mg. So far, so good. I have voltage, I have distance between the plates, I have force due to, or acceleration due to gravity. I still don't have mass. Need a third formula. The mass is related to the density. Density equals mass over, and I'm going to write volume because we're using potential difference here, so I don't want to mix up the two capital V's. So we can get the mass by multiplying density times volume. So mass equals density times volume. Now, we make the assumption that this is a perfect sphere, so we need a fourth equation. The volume is equal to 4/3 pi r cubed. Now, you may be wondering, where are these formulas on your data sheet? They would be provided to you in the question if this was the amount of calculations you would be given. Every time I've seen these, they've given the density formula, they've given the volume formula, so it's not something you have to memorize. Any formula required in the course that's not on your formula sheet will be provided in your questions. Now, this means I'm going to put together equations 3 and 4. So I'm going to substitute 4 into 3. So equation 3 becomes mass equals density times volume 4/3 pi r cubed. And finally, I could substitute equation 3 into 1 and get my final formula here for Q. Before I do that, I'm going to manipulate 1 as is. I'm going to multiply by D and I'll divide by V. So this Q will be equal to, I'm going to go G times D times the mass, which is density, times volume, 4/3 pi r cubed. So it's gravity times distance between the plates times density times the volume divided by voltage. There's our final formula that we're going to do our substitution into. Fairly complicated, just like how Millikan worked through it. He had to use 4 different formulas. We had to use 4 different formulas before we finally got one variable unknown in our formula. We know G, we know D, we know P, we know R, we know voltage. So I'm going to do this substitution on the next slide. Again, if you're finding that it's quite complicated to do this many substitutions, and this is probably one of the more difficult ones you'd see, maybe work out the volume separately, then work out the mass separately, then work out the electric field separately, and then substitute those answers back into the original if needed. However it works for you is fine. You're not given extra credit one way or another as long as you show your work along the way. The only reason why I do it this way is it tends to involve the least amount of rounding, so my answer should be as accurate as possible. So on the next slide, let's write the formula again. Q equals GDP. GDP times 4/3 pi r cubed divided by V. And let's put in all these numbers. Q equals 9.81 meters per second squared times the distance between the plates. I'll have to keep bouncing back and forth here. 30 centimeters or 0.3 meters. The density was 1.35 kilograms per meter cubed times the volume, 4/3 times pi times the radius, which I'm going to write as 1/2 times 6.05 times 10 to the negative 6. Don't forget to cube that number. Divide that by the voltage, which should be 240 volts. And now we just got to be very careful on how we enter this into our calculator. I'm going to work out what the 4/3 pi r cubed is first. 4 divided by 3 times pi times 0.5 times 6.05 to the exponent negative 6 to the power 3. Work out the volume times by 1.35 times by 0.3 times by 9.81. Divide that answer by 240. And we should get here a Q value. Let me jot this down. Our charge will work out to 1.92 times 10 to the negative 18 coulombs. So to find the number of charges, this will be equal to 1.92 times 10 to the negative 18 coulombs, again multiplied by 1 charge for 1.60 times 10 to the negative 19 coulombs, and you get the number of charges. This should be very close to a whole number. Divide this by 1.6 to the exponent negative 19, and you get 11.99 or 12 charges. We do not know if this is negative or positive yet. I'll have to go back to my diagram to check it. But again, just a reminder, if you're finding number of charges, you're basically taking your total charge, dividing by the elementary charge off your data sheet to find the number of individual charges. If you go back to your picture, notice the top plate being negative. So to have an electric force upward, that means that this thing would have had to have been positively charged. So this is positively charged. Doesn't ask us to say that, but it's just for us to make sure that we understand the question. This would have had to have lost 12 electrons to be positively charged, and then would have experienced this scenario for this question. It was positively charged to have that attraction to the top plate.